ultimately of our enantiomers. So there are a couple examples up there. And one of the issues that we find with our enantiomers is that in most cases, their physical properties are identical. So their melting points are the same, their boiling points are the same, which makes them very difficult to separate. Okay? Their solubilities are ultimately going to be the same. And where we can really come up with that differentiation and allowing us to separate these actually comes in what might be kind of an obvious format. Okay? Is there a difference between these two structures on the left? Yeah, what's that difference? Could look at mirror image, but to figure out that they're mirror images, you would have to see the structure. Pretty sure none of us can see the structures unless we draw them. So we can't actually physically grab that molecule and look at it to figure out what it is. How else could we tell the difference? There's no resonance in this, and resonance, again, only involves with the structure. We can't see the structure. You can't see that molecule. How could you tell the difference between them? You can smell them. Okay? On the left, one smells like citrus, the other one smells like turpentine. That's a pretty drastic difference in smell. Okay? We can sort of indirectly take advantage of that property as a way to try and separate them. Instead of separating them based on kind of bulk physical states, what we can go through and do is have them interact with another molecule. That other molecule will be chiral. Okay? That's going to allow for a preferential interaction between our new chiral molecule and what we're trying to separate. Okay? So really the only way to separate enantiomers is to have them interact with something else that's chiral, which is a bit problematic. So in a synthesis experiment, if we were going to make or run an individual reaction, what we want to do is make sure that we don't have a reaction that generates enantiomers as products, because it's very difficult to separate them without going through a bunch of other steps. Okay? And as we find in lab, the more steps we do, what happens to our yield? And it goes down. Okay? So we want to limit our exposure as much as possible. So a lot of the chemistry that we'll talk about focuses around making only one enantiomer. So we get chirally pure systems. The other way that we can avoid this whole enantiomer separation issue, work with structures that don't have chiral centers. Okay? So there's a lot of chemists that will only focus on, or not necessarily only focus on intentionally, but will only look at structures or work with structures that don't have chiral centers in them. So that can simplify a lot of the chemistry that we would deal with. Okay? So as far as separating them, so this is kind of where we can go through our options. Don't make them, okay, which is the one we're talking about already. We want to make sure that our experimental design is set up such that we don't make both of them. We only make one of them. Okay? If we can't do that, then we're forced into a different situation. We can separate them on a chiral medium. So we can introduce a third species that is optically pure, that is enantiotopically pure. So there's only one chiral version in it. That will then preferentially react with one of our enantiomers, and we can then separate it out based on that interaction. Okay? It's ultimately what we're doing when we smell it. Okay? What we're separating is our receptors. Our smell receptors are chiral, and will only interact with one chiral version over the other. Okay? So you get slightly different interactions because of that. Yeah.
You said the third species that you introduced is chirally pure?
It has to be chirally pure. Yep. The other thing that we could go through and do, and this is almost a derivative of step 2, is that we can actually do a chemical reaction with a chirally pure compound. So in step 2, we're introducing this third compound that allows us to kind of separate. So we could look at a solvent almost and look for solubility. In step 3, we're actually doing a chemical reaction. That chemical reaction is going to change the structure a little bit, and what we're hoping is that we get a new or a way to separate these. Okay, so if we start with our enantiomers to begin with, okay, our enantiomers on the left, I'm sure that sigh went through in the recording too. Our enantiomers on our left there. Okay, what we want to do is react them with something chirally pure. So the standard to use would be something like RR tartaric acid. So RR is referring to the chiral centers in tartaric acid. So those now red dots. Those positions, if you assign their RS stereochemistry, are both R. Okay? And we isolate that as an enantiomerically pure compound. So we just get the RR version. We have no other types in that compound. We then react that with our enantiomeric mixture. Okay, in the process of doing that, we're going to run an acid-base reaction. The nitrogen, excuse me, our nitrogen carries a positive charge, and then our tartaric acid carboxyl group will carry a negative charge. What type of bond is between those two atoms? It's an ionic bond. What's another name for an ionic compound? It's an electrostatic force. What's the other name for the compound? It's your classic example of an ionic compound.
Salt.
Salt. So what we've got here is a salt. Okay? And we're going to end up with two salts. What's the relationship between those salts? Well, the conjugate would be looking at comparing across the reaction. We're comparing just our two possible products. They're not identical. Okay. If we tried to superimpose, let's take the bottom one and superimpose it. It's not superimposable because the amine is aimed the nitrogen is aimed the wrong direction. So we could try and flip it over so the nitrogen is aimed in the right direction, but now they can't overlap. What's the relationship between these two? Are they mirror images? The amine absolutely is a mirror image. What happened to the tartaric acid? It's the same. We didn't change the chiral centers around the tartaric acid. What's the relationship between these two structures? They're diastereomers. They're not enantiomers. They're not identical. We're looking at diastereomers. Why is that important? What's different about our diastereomers, particularly in their physical properties? They are different. Okay? So if we can generate diastereomers, we can now separate them because the physical properties have changed. Okay? Not the easiest method. We try to not do it, but it does work. We can now separate these two salts based on their solubilities, because their solubilities will be slightly different because of that slight tweaking in the arrangement. Yeah?
You said what is that again? The nitrogen containing?
The nitrogen, it's an amine.
Okay, so
I meant to say just nitrogen.
The amines are diastereomers?
The amines are enantiomers of each
Right.
other. Okay, if we real quickly assign that, that's 1, 2, 3. Right? Yeah, so this one's R and this one's S. So if we go in and take a look at this, we've got R, R, R for those chiral centers. What happens when we go through with the other salt? S, R, R. For them to be enantiomers, what's the relationship? All of them have to exchange. Do all of them exchange? No. All right. So our relationship now between these two salts is that they are diastereomers. Because they are now diastereomers, we can actually separate these two.
Oh, you're looking at the combination of the two.
Yeah.
I thought you were looking at the individually with each other.
That's why I was trying to put the brackets on
right.
that. So what we're looking at is this compound versus this compound.
Okay, yeah, that makes sense. Sorry.
So the second thing is identical in both of them, right?
The second component within each of those salts is identical.
Really
Yeah.
identical.
But-
I couldn't get it.
But what you have to realize is we can't separate those away from each other because it's now a salt, so they are directly linked to each other.
Gotcha.
So the bottom.
So, sorry.
Maybe he's gonna ask the question.
So the bottom one won't react to the top one? That's how you separate it.
We'll see some version of that. So one will react, they will now react differently with solubility or melting points, boiling points, and we can try and separate them that way.
Yeah, that's what I was gonna say, because
Yeah.
they have a different chiral orientation.
Exactly right.
One, you can now separate these based on one.
Yep.
Something,
Yep. Our standard physical phases are now different.
whereas before,
Whereas with our enantiomers, we don't have a difference in how they organize. Okay? They're just going to organize the opposite direction of each other. But ultimately the same. So we could look at +1 versus -1. Okay, so they're just doing the opposite, but the magnitude is ultimately the same. Okay, we don't have a way of separating that. Okay? So it's kind of an interesting property. We don't have to stress too much about it, but we ultimately have now our diastereomers, and now we could separate them. Okay? The next thing isn't really actually separating them, but it's admitting that you can't separate them. And in that case, we need to be able to report that we can't separate them, or that we didn't separate them. That reporting gets done as an enantiomeric excess. Okay, so to calculate the enantiomeric excess, it's going to be the percent of our highest enantiomer, whichever one that one is, minus that of our lowest. Okay? Which means our enantiomeric excess should almost always be what magnitude, positive or negative? Should always be positive, okay, depending on what we're looking at. But it could be positive R in excess or positive S in excess. So you have to be very careful in realizing that your positive value is going to be in direct reference to whichever one was in highest excess. Okay? Questions on that? Unfortunately, we will be coming back to number 4 and actually looking at some math with that too. Let's step actually back from that. How do we figure out what our percentages are? That becomes a little bit more challenging. Okay, most of our spectroscopic forms aren't going to allow us to differentiate between those two, at least as far as you guys are concerned right now. Okay, so we don't have a clean way to quickly analyze this data and look at an individual solution to say, oh, this one it's 60% this one and 40% this one. Okay, we can't figure that out. So we need to come up with some lab method that allows us to observe which chiral atom we have. Okay, that lab method has to do with polarity. Okay. Anybody used polarized sunglasses? Okay. Fairly common. Anybody taken 2 polarized sunglasses and bring them near each other, overlap the lenses, and then start to rotate? What happens to the light? Goes away. Okay. Polarized lenses remove half of the light. Okay. That's the whole point of the polarization. So if you take your 2 lenses and you start to rotate them around each other, what you can do is ultimately line them up. So one lens removes 1/2 of the light, and the other lens removes the other half of the light, and now no light passes through. Okay? So what we're going to go through and do is see how light can interact with these molecules. Because if we can make polarized lenses, very clearly lights can interact with molecules differently. Okay? Because we have an ability to filter out half of it. Turns out chiral molecules will interact with light differently. But we have to be very careful with our setup so that we can actually quantify it. So what we're going to do is set something up along these lines. We're going to start with a sodium lamp, and then we're going to put a monochromator on it. What does monochromator mean? One light, ultimately, or one color. So what we're going to do is take that sodium light, and we're going to filter out most of it so that we only have one wavelength to work with. Okay? We're then going to pass it through a polarizing filter. So what they're attempting to show in that middle little orange wheel is that when our light passes through that first filter, our light is aimed every which direction. Okay? It's a wave. It's coming out, and we could look at the vector of the light being all directions. We're then going to pass that light through the polarizing filter. That filter is only going to allow light that is on that vertical axis to pass through. So anything that is off of that vertical axis gets trapped by our filter. So if we look at the result after our filtration, what happens? Our light now is only in that vertical axis. Okay, the light is going to stay in that axis. It's not going to rotate off of that axis until something forces it to rotate off. Okay? That forcing is now our sample holder. Within that sample, if we have an achiral molecule, so no chiral centers, what's going to happen to the light? It's going to pass straight through, which means the light does not change off its axis. It still runs straight through the sample, and we still get that vertical result. What happens if there's a chiral molecule in there? Well, now light comes up and sees that chiral molecule and goes, oh, you're twisted a little bit to the right, so I'm going to twist a little bit that way too. Okay? So the light starts to shift off that axis. Then it encounters another molecule just like it, and what happens? It shifts a little more off axis. And it hits another molecule and shifts a little bit more. And it's going to continue to shift off that exact same axis degree because those molecules are all the same. We're dealing with that pure chiral molecule. What we can then do is set up a detector at the very end of our sample. And what we'll do with that detector is look at how far the light was rotated off of that 0 axis. And then we can report that number as something to do with our sample, our chiral sample. Okay? What we're going to end up reporting it as is either a positive or a negative. Okay? Positive because we rotated towards positive degrees when we rotated our detector. Okay? Or negative because we rotated at negative degrees when we looked at our detector. Okay? Turns out positives and negatives, where's your negative typically found? On the left. Okay, so if we're going to rotate something to the left, anybody know what that's referred to? Could go counterclockwise, I'll accept that. I want to avoid counterclockwise, and it's not S. We have to be careful with that.
Lefty loosey.
Levorotatory.
That's like lefty.
Okay. Levo for left. Okay, we're turning it towards the left direction, so that's our negative. Our positive value, we're rotating on which side of our axis is our positive value typically found? On our right-hand side. We're rotating it to the right, also known as dextrorotatory. Okay? So what we're looking is how the light is shifted off that 0 axis. Okay? Our sample is going to cause it to rotate. If it's an achiral molecule, the light doesn't rotate, passes straight through, and we would get a 0 for our reading, which means there's no directionality to it. If our molecule is chiral and pure as that chiral system, it's going to rotate one direction or the other. Which direction does it rotate? It's a coin toss. Okay? If we know nothing about that molecule, it's going to rotate one way or the other, and we could now report it. Okay? So we could look at, say, glucose. You guys heard of glucose? Okay, what different forms of glucose are there? You heard of D-glucose, L-glucose? What do the D and the L stand for? Dextrorotatory, levorotatory. Okay. It's ultimately looking at how light interacted with that particular form of glucose. Because if you look at the form of glucose, okay, go back home and look at your structure for glucose, there's a ton of chiral atoms within that structure. Those chiral atoms are causing the light to shift off axis. And in the case of D-glucose, the net is that the light is rotated towards our positive values, our dextrorotatory. Okay? If we looked at L-glucose, it's rotating it to the left. Okay? We could also, instead of referring to those as D and L, we could refer to them as positive and negative. Yes?
Would it ever happen if the light was passing through, it starts rotating to the right, and then it goes back to the left, and then the correction?
Yes, we'll talk about that in a little bit, though. Okay? So what we're referring to in this case is something known as optical activity. Does our sample have optical activity? If it is an optically active sample, what does that mean about the molecule? It is chiral. If it is optically inactive, what does that mean? It's achiral. Okay, so it's allowing us to interpret that without actually being able to see what structure we're looking at. We could look at some random solution that we pulled out of nowhere, put it into our sample detector, and fire it off at it. See what happens. Okay, and we could say, oh, that molecule is chiral. I don't know what it is, but it's chiral. Okay? If I went through and made or did a reaction where I made a compound and I wanted to find out if my compound was chiral or not, I could throw it into this instrument and say, okay, was it chiral or not? Okay. Did I make enantiomers? So that's the next question. Okay. If in the process of running my reaction I made both enantiomers, what happens to the optical activity?
Should it be center out?
It's going to zero out. Okay? One version of our enantiomer will rotate the light one direction. The other version, being exactly identical except that we change the location of ultimately one bond, will rotate the light the other direction. So if I generated a mixture that was 0% enantiomerically pure, meaning it's 50-50 of both my enantiomers, I expect to see no light rotation. Okay? Because our light is going to interact the complete opposite of that type of stereo center. Kind of, sort of? Okay. The majority are saying yes, I'll accept that. Next big issue on this. R and S are very, very similar or easily confused with this. There's a reason why I did not call this clockwise and counterclockwise. And the reason being is that with our clockwise and counterclockwise, we use that terminology to come up with R and S. Okay? Why did I not use clockwise to describe dextrorotatory? Because dextrorotatory will give me a D or positive designation. That does not mean it's R. R and S are an absolute configuration. Okay? That is, given the structure, I know absolutely the orientation of those atoms. Okay? Because I followed those Kahn-Ingold pre-log rules. Optical activity allows us to understand something about how it interacts with light, but it's not the absolute configuration. Okay? It's going to refer to our specific rotation, how it's interacting with light. So it gives us information about that it is chiral, but it doesn't necessarily translate over into the RS system. Okay? Why does that become particularly irritating? Because I say not necessarily. Sometimes it matches, sometimes it doesn't. Okay? Which means it's very easy for students when you read through it to say, oh, this one was D and they're labeled it as R, so that means every time it's D, it's R. No. It just happened in that one case that since it was labeled D and R, they happen to match. Okay? So you got to be careful with that. They are two entirely separate systems. So if I tell you you have L-glucose, what's its absolute configuration? You have no idea. Right? So on a multiple choice exam, what you could probably see is you're given L-glucose. Define its absolute configuration. Okay? R, S, can't tell. Can't tell. Okay? So you have to realize optical activity and your RS system do not overlap. Keep them separate. Oh, shoot. That's what this was going to say. Okay? So again, on our R enantiomer and S enantiomer, we don't necessarily know whether it's going to rotate positive or negative. Okay? But let's assume. Okay? So now we're going to add a little bit more information to this. I tell you have an R enantiomer, and it rotates light in the positive direction by 10 degrees. If I now take the exact same amount of the S enantiomer in the exact same conditions as I had the R enantiomer, what's the rotation going to be? It's going to be a negative 10 degrees. Okay? So they will necessarily be opposites of each other. But it doesn't mean that because it's positive, it's R. Okay? So the converse example. So this was one possibility. I give you another possibility, and I say instead, we have the S enantiomer, and we notice that it rotates light positive, 53 degrees. I now take an identical amount of my R enantiomer, and I test its optical activity. What's its result? Negative 53 degrees. Okay? So we can't tell or correlate our positives with R or S necessarily, but we do know that they are the complete opposites. Okay? Makes sense? Okay, so the next part about this is where do we get these numbers? So that rotation, I don't want you to look at that quite yet. What is going to be dependent on that rotation? Okay, we said when the light comes into the sample, it hits and it rotates as soon as it hits that molecule. What happens when it sees another molecule? Rotates again. And another molecule? Rotates again. What things are going to determine how much it rotated? How many molecules there are, which is ultimately described as a concentration. Okay? So what we need to do is standardize our results. Because if I take a sample and say it rotates light by 52 degrees, and you take a sample and it rotates light 15 degrees, that doesn't mean those two compounds are different, but it means our experiments were different. The experimental difference could just be concentration. Mine could have been twice as concentrated or 3 times as concentrated. And yours just being a little bit less concentrated won't rotate light as much. Okay? So we have to come up with some way to standardize, just like we do with our percent yields. Okay? So we'll look at an observed rotation and then a specific rotation. Okay? Characteristic to now being standardized to the solution concentration. Is it only the concentration that's going to matter? Okay? No. What else could matter?
Other physical properties, and if it's
No, not even that. Let's say you take this sample. Okay, let's draw a couple samples here. There's our particular sample holder, and you put in 4 units. Okay? I'm going to take a sample holder,
size of this.
and I'm going to make it much, much longer. And I could put in those same 4 units. Would I expect the same rotation?
No.
Not necessarily. Okay? So it's not just the concentration, it's also the size of our sample holder. Okay? And ultimately what we're concerned about is not necessarily the size, but the length that the light has to pass through. Okay? So what we've got is a way to convert our observed rotation, which is given this alpha symbol, so our alpha observed, and we'll divide that by the concentration of our sample and the path length, okay, which is our L value. That allows us to convert our observed rotation or standardize it into a general format so that if I take it, the rotation here and then use a different instrument somewhere else with a different concentration, I can get the same result, the same specific rotation for that compound. Because a particular molecule will always rotate it the exact same direction. Okay? Some little caveats along those lines. The observed rotation is something that would be pulled directly out of the instrument. Okay? There's no calculation involved with that. The concentration does involve a calculation, potentially. You'll notice that it's not the standard concentration that we're used to. Most concentrations we work with are what units? Moles per liter, molarity. In this case, the units are grams of the compound per milliliter of solvent. Why do we use a different unit? It's ultimately how the sample was made. Right? Every time you see a new unit, that's because somebody else discovered that information and then we try to compile it all together. Okay? So in the case of optical activity, what we ended up doing was somebody took a certain mass of the compound, diluted it to a certain volume, and then tested it. Because they were the first one to do it, they got to decide what units were used, regardless of what other things we learned. Okay? The path length is reported in decimeters, okay? And it is typically 1 decimeter. Why is that nice? Whatever your number is, you divide it by the path length, what is it? Same number. Okay? So that's at least kind of standardized out kind of nicely. So if we change the path length, we'll change our observed rotation. If we change the concentration, we'll also change our observed rotation. We take all of those variables and kind of put them together and cancel each other out such that we get one specific rotation for a particular compound. Okay, that will then be characteristic for that compound. We don't have to worry about where we're observing it or anything along those lines. We'll get the same answer. All right? Yes?
The size, the bracket means concentration.
The brackets, I actually left some stuff off it because it's not necessary. The brackets is just kind of the standard format. Usually they give you a wavelength, and they give you a D. No. Sorry. Temperature. They tell you a degrees Celsius, because if you change the temperature, you're going to change how the molecules are moving, potentially change how the light interacts with it. So you have to report it with respect to a particular temperature. and the D stands for what light you use to excite it. Okay, when it comes to polarimetry, almost everything is used using the sodium lamp, okay, and it's typically referred to as D because we use the sodium D line. If you look at the atomic or the light spectrum, the atomic light emission spectrum for sodium, we're using the D line of it. So someone went through and alphabetized those or named them. Okay, so you might see that extra information specified when you look at your specific rotation. The brackets are really there just to delineate and say that's specific rotation, not your observed. Okay? Questions on that? Okay, so let's take a look at some potential calculations with this. Which of the following should show optical activity? All right, so I'll let you think about it, talk to each other, and then we'll come back and A should show optical activity. What about meso?
Depends.
Remember that flow chart? Where is meso located?
Under identical.
Under identical. Where is chiral located? Way the other direction away from identical. A meso compound has chiral atoms,
Right.
but it's not chiral. Okay? One way that you could go through and evaluate that is one of those will be R, I'm not sure if I did that right, and the other one comes out being S. So our light comes through, sees the R, rotates. What does it then move into? The S, and rotates right back the opposite direction to nothing. And we end up seeing no optical activity for a meso compound.
You can have a meso compound that has two R chiral, that would be meso.
Yeah, that would be your issue.
And it'd be
Yeah.
okay.
How about a mixture of enantiomers? 1 to 3, S to R.
Yes.
Yeah. Okay, it's going to rotate based on our R enantiomer because our R enantiomer is in excess. So our light passes through, sees the S 1 time, sees the R 3 times. Okay, so we'd see a net rotation due to 2 R's. Yeah.
So to find the total rotation for the R, you have to take into account and subtract the rotation of the S.
Yes, which we'll look at. What about a mixture of enantiomers? Okay, in this case, it's 1 to 1. No optical activity. It encounters one enantiomer, rotates, encounters the other enantiomer, and immediately rotates right back. Okay? A mixture of enantiomers, in this particular case, this 1 to 1 ratio, also carries another name. Right? I'm sure you all read the book, so you know what that name is. What's that book? What's the name? It's a racemic mixture, okay, which can also be referred to as racemate. Okay, when you see that RAC, blah, 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 you're looking at a 50-50 mixture. Okay. Last one, a mixture that has 0% enantiomeric excess? No. That's the same thing as D. Okay, 1 to 1 ratio. So 50% of it is R, 50% of it is S. So if we try and calculate our enantiomeric excess, we get 50 minus 50 gives us 0. Okay, so no optical activity on that one either. These are really good questions, by the way, as far as multiple choice go. We've got already 5 options up here. Okay, and we just talked about adding in 2 or 3 other possible definitions from these. Okay, so you will see questions on optical activity easily within your multiple choice. Oops. If it is pure, if it is 100% R, what's our enantiomeric excess? So it's 100% R minus 0% S. What's our enantiomeric excess? It's 100%. Okay, so a pure solution has 100% enantiomeric excess because it is 100% more than our other one. Okay? So the last slide on this, I'm not a big fan of showing this calculation, but I'm sure it's going to show up every so often, so I at least want to go through it. It's kind of more of an advanced question. We can also solve for the enantiomeric excess by looking at the optical activity. Okay? We don't have to go through and do our percents. Okay? So if we are given our optical activity of a mixture, an unknown mixture, and we compare that to the optical activity of the pure enantiomer, we can figure out our percent enantiomeric excess. Okay, what do I mean? Well, let's say we have the enantiomerically pure system, okay, has a rotation that is positive 15. And I take a look at the mixture, and the mixture says positive 15. What's my enantiomeric excess? 100%. Does it make sense to be 100%? If it's pure, I should expect the exact same optical activity. Okay? What happens if instead of being positive, I get negative 15? What does that mean? It's 100% excess, but it's of the opposite enantiomer. Okay? So we can look at this balance to be able to figure this out. Okay? So let's take a look at the next question. The specific rotation of 2s iodobutane is positive 15.9 degrees. Okay? Determine the composition of an enantiomeric mixture of 2-iodobutane. You notice we haven't specified whether R or S in this case because it's a mixture. If the specific rotation for the mixture is negative 3.18 degrees. Okay? It's going to involve a little bit of algebra and ultimately trying to convert those numbers into an appropriate equation. Okay? Can we determine the enantiomeric excess? Well, let's step away from that actually. What are we asked to solve for? The percent composition. So I want to know the percent R and the percent S. Okay, I want a number for each of those values. Okay. Based on the numbers given, what can I calculate?
Rotation of R.
I could determine the rotation for pure R, but that doesn't tell me anything about the percent composition. To figure out the percent composition, okay, percent of our highest minus the percent of our lowest, right? We would need to know the enantiomeric excess. Can I calculate the enantiomeric excess? Enantiomeric excess is equal to
specific
the mixture, negative 3.18, divided by
plus 15.9.
our pure, plus 15.9.
So we could find percent of R since it's negative.
We're going to end up with a negative value, okay, and this is where we got to be careful in keeping track of all of these things. Our positive 15.9 was for the S, which means when we get a negative value, whatever that number may be, what we're saying is that that is the excess of our R. So we can get rid of the minus by saying excess of R. Okay, anybody got a number for me? So we are looking at a 20% excess of R. Oh, I got 20% and R in the same sequence. Can I put in 20 here? Is my percent R 20%? No, it's the excess. Okay? So what we're saying for our excess, whoops, is that our excess now is 20% of our R, which is going to be equal the percent of our R minus the percent of our S. That looks like one equation and one unknown, or two unknowns. How can I solve for R and S?
Solve for R and then plug it back in.
How do I solve for R?
Move over S and then go back.
Well, it's still going to keep both variables in there. No, because that assumes that our answer is 0, and we'd have 100% of one of them. Our total percentage has to be 100%. So 100% must equal R plus S.
Then you just do the system equation.
Now we can set up our solving for R, plug that in, and we can determine what our answer would be. Okay? If I remember right when you go through and do the calculations, 60-40. You get 60% R, 40% S. If we look at our excess, yeah, that gets us our 20%. So the answer in that case ends up being 60% R, 40% S. Okay. So the linchpin, in my opinion, is realizing that last equation, that total, the 100%, has to be composed of just our R and our S. Once we've got that equation, now everything is just a system of equations, just plug it in and solve. Okay. Questions on that? Okay. Not a super big important one, which is why I don't want to spend a whole lot more time on going through and solving something to this extent. You will be held responsible for this, but no more than one question looking at something at this kind of difficulty. Okay? Help delineate the difference between our A's and B's. You guys still writing stuff down? Or am I good to move on? I'm going to move on then. What we're going to move into is chapter 13 and 14. The one thing we haven't talked about in 13 is mass spec, and then 14 is our NMR. So in that initial video that I posted online, I went through the details on solving each of these things, less information about what is actually happening within them. So what we'll talk about in these cases is more along the lines of what's happening within them. And mass spec, effectively what you should imagine it is that we take a whole bunch of our molecules, we put it into our instrument, and then we blow them up. That's mass spec. Okay? You blow up those your molecules into tons of tiny little pieces. Okay? And the process of doing that, we can then analyze the pieces. Okay? So we'll pass those pieces then through a separation scheme. Okay? And in that separation, it's going to separate them based on their atomic weight. The smaller the particle, the more it's going to move, or the faster it's going to move. So we will then space out where we blew up our particles and where we've got a detector, and we can effectively relate the time that it took to hit the detector back to the mass of the particle. Okay, and all our detectors are going to do is just sit there and count. Yep, particle hit, particle hit, particle hit, particle hit. Okay, and it will then kind of average that out and give us data for how many particles hit at that particular instant, which is going to give me a peak for that mass of particles. Okay, so our mass spec allows us to determine the mass of our molecule and ultimately all the pieces that went into it. Okay. The analysis that I used in the video was ultimately looking at someone like CSI. Okay, a CSI detective goes through and tries to analyze a bomb. Okay, something that's already blown up, and they want to figure out who made the bomb, why they made it, where they put it, how they stored it, all of those different things, they can slowly piece together out of the exploded results. Because where the bomb was centrally located, we would probably expect to find the most tiny little pieces, because that's where everything was completely detonated. We're doing a similar idea when we look at mass spec. We're looking at all those little pieces, and only trying to take them and put them all back together to get us an idea of what the structure was. And one of the things that we're going to rely on when we're dealing with this is that our molecules will break apart in very predictable fashions. And that's going to have to do with how we go through and blow them apart. What's going to happen is we put our sample down and then we ionize it. So we're going to fire a high energy electron at our structure. So this is what's happening on the reactant side. We've got our high energy electron. That says energy. And our target molecule. That electron comes speeding by so fast that when it hits the molecule, it hits another electron, and they both go flying out of the structure. Okay, at this point, our molecule now becomes charged. Okay, why has it become charged? Just lost an electron, so it's now positively charged. Depending on what electron was lost, we're going to see a slightly different molecule. So in the very first, or the top section up here, what we're looking at is losing probably an internal electron, because we're maintaining the bonding structure. So what happened to the mass of that molecule? It didn't change. It is the exact same weight as what we started with. okay? Which is probably going to be the biggest mass. Why would it be the biggest mass in our detector?
It's the initial mass.
It's the initial mass. What happens in mass spec? It blows everything up. Everything gets smaller. Very rarely do we see things get bigger. It can happen, but not very often. Okay, I won't test you on those. So what we've got here is what's known as the molecular ion, usually written as M for the molecular or the molecule, but it's charged. What's its charge? Plus. We have the M plus peak. Because this is the biggest possible piece that we could get, this signal is typically found to the furthest right in our mass spec, at the highest M to Z ratio. What does M to Z stand for? Mass to charge. Our separation scheme in that previous slide is separating based on charge. It's looking for that positive charge. And we weed out all the other particles that aren't charged. So it kind of refines our cleaning process. So when we go through and look at this, we now have, whoops, that's going to move. We now have a way to identify the molecular weight of our compound based on our spectra. So we find the peak furthest to the right, that's our molecular ion peak. Okay? However, is it always the peak furthest to the right? No, why not? What else is going on?
Could be another peak like within 3 units.
Why within 3 units? Why is it not just the peak furthest to the right? What we are looking at is a random sample of this molecule. In this random sample, it's not just hydrogen, it's also deuterium. The heck is deuterium? It's hydrogen with an extra neutron. So it has the exact same chemical nature, but what has changed? Its mass. In this same sample, not only do I have a different isotope of hydrogen, I also have different isotopes of carbon. Okay, which means those could potentially have an additive effect, and we could end up seeing a peak a little bit further to the right from our molecular ion peak. So in the discussion, to identify your molecular ion, you find the peak furthest to the right, and then you find the tallest peak within 3 units of that. Right? That will be your molecular ion peak. Right? That tells you the mass of your compound. And it's going to tell you the mass of the most common isotopes. Okay? It'll be the mass of hydrogen as a mass of 1. Carbon as a mass of 12. Oxygen as a mass of 16. Bromine as a mass of 79. 79 is the most common isotope weight for bromine. Okay? And we take advantage of that because what's special about bromine? Its second isotope has a mass of 81. What's the percent composition of the total isotopes? Roughly 1 to 1. So when we look at the mass spec with a compound with bromine in it, we see an extra signal, a peak a little bit further to the right by 2 units. Those 2 units are the 2 neutrons that bromine 79 accepted to become bromine 81. So if you see those 2 peaks, you now know bromine was present in your molecule. Okay, so it can help you identify what's going on within your structure. Does it have to eject an electron from the middle of the structure? No, it could potentially eject that electron from a bond. If we eject an electron from the bond, what happens? What happens to the bond? It breaks. No longer present. So what we're looking at in the next 2 examples is removing an electron from one of those bonds. In that blue case, we're looking at removing the electron between the hydrogen and the carbon. In that process, we generate a hydrogen radical and then that carbon cation, okay, that positive charge. How did we detect our molecular weights? Charged particles. If this impact actually occurred, I would expect to see a signal for the mass of that piece. Would I see a signal for the mass of that piece, of our hydrogen radical? What do we detect on our detector? The charged pieces. Is a hydrogen radical charged? No, we don't see a signal for the hydrogen radical because it's not charged. It gets filtered out of our analysis. Right? What happens in the last case? Where was the electron ejected? from our carbon-carbon bond. And we again end up now with two pieces, okay? A methyl cation and a methyl radical. The methyl radical gets filtered out. We don't see that hit our detector, and our methyl cation hits the detector. And I now see a peak for the mass of that piece. What is the mass of this piece? 15. Carbon is 12 plus 1 for each of the hydrogens. We've got a peak at 15 for that piece. Okay? So this could get a bit cumbersome to analyze because our electron could be ejected ultimately anywhere within the structure. So we could expect all sorts of possible arrays. We might expect a peak for every single thing. Okay? Except our molecules are going to break apart in fairly characteristic patterns. Remember, the electrons can ultimately kind of shift around a little bit within the structure. Once we form or once we eject an electron, the molecule can decide how it wants to break. Does it want to break such that the hydrogen comes off as a cation, or does it want to break such that our carbon comes off as a cation? Which one gets the electron? Okay. In this case, hydrogen gets the electron. So we need to come up with some way to predict that. Okay. That prediction ability, okay, is going to show up here in just a couple slides. Okay. What I expect to get out of mass spec is what was summarized within that video. Okay. The very first thing, we find that M plus peak. The next thing that we could look at is if that M plus peak is odd, then we have an odd number of nitrogens. And that's because when we put hydrogens onto our nitrogen, it gives us a different ratio than it does if we were carbon or oxygen. Okay, both carbon and oxygen put on odd numbers of hydrogen, whereas our nitrogen puts on an even number. So it shifts our molecular weight around. The next thing we could look for are those isotope effects. There's really only two isotope effects that you should be concerned about. That's bromine, which we already talked about. So we look for the molecular ion peak plus 2 neutrons, which typically gets referred to as the M plus 2, okay? Because it's still positive and we have that extra 2 neutron mass. If the ratio in those two peaks those two peaks are the same height, we're looking at bromine being present in the molecule. If the relationship between those two heights, I'm not good at fractions, so let me adjust the next one, ends up being 3 to 1, then we have chlorine. Okay. Why is it 3 to 1 and not 1 to 1? It has to do with the isotopic abundance of chlorine 35 versus chlorine 37. Okay. And it turns out the 35 is slightly more abundant. How would you be able to figure that out? How do you know chlorine 35 is more abundant than 37?
Mass is closest to 35.
Take a look at the mass off the periodic table. Which is it closer to, 35 or 37? 35. 35 is our higher priority, or our higher amount. The very last thing that we can look for is iodine. Very, very rare for it to show up, but if it does show up, we would expect a massive molecular ion peak. Why should it be so big? Because iodine is freaking big. Okay? So if we're going to look at a molecule that has iodine in it, the mass is going to drastically go up because iodine is so massive. The last thing we could look for within that is that iodine, not only is it so big, but it can actually lose an electron pretty readily, and we can form the iodine cation. Right? If we form the iodine cation on its own, we're going to see a signal at 127. Okay? Why 127? That's the mass of iodine. Okay? So those would be the things that we could look for. The next part of this why did I stop? Is looking at the fragmentation patterns. So how can the molecule possibly break apart? I said there's got to be some rules behind it. Well, those rules are going to be determined by the stability of those pieces. And the stability that we're really going to evaluate is the stability of the carbocation. So we need to come up with some way to understand what makes a stable carbocation, what makes an unstable carbocation. Okay, what do you think might make a stable carbocation? If it can hold the charge, how could it hold the charge? Would a highly electronegative atom hold a positive charge very well? No, because highly electronegative atoms want electrons. Okay, so we wouldn't expect high electronegative elements to pick up positive charge. Okay, so we would expect the lower end, so we would probably see carbon or hydrogens potentially holding positive charge. The other thing that we could evaluate within that, resonance. Is there resonance? Can we push electrons around through the structure to stabilize that positive charge? Can we put that positive somewhere else in the structure? Okay? If we can delocalize it, we've stabilized it. So let's take a look at some general problems here. We've got, and we can ignore the radicals, though they're ultimately the same kind of idea as our cations. What makes each of, well, first off, are these four things different? What's different about them? Number of carbons. That bottom one is typically referred to as what kind of carbocation? Tertiary, because it's bound to 3 carbons. What makes each of these species unstable? The charge, okay, the positive charge. Okay, so they're all positively charged. Is any one of those more or less stable than the others? Why is the tertiary more stable than the others? Why is being bound to more carbons important?
Well, it's resonance, right?
There's no resonance. It's known as an inductive effect.
There's more electrons around each carbon.
How many electrons are around our carbocation? So to stabilize it, we want to give it as many electrons as possible. So where's the closest source of electrons around each of these cations? The bond. How many electrons are in each of those bonds? 2. So in that first one, our primary, or sorry, I'm going to call it zeroary. We've got 6 electrons around it to stabilize it. Cool, that's a good number. I like that number. Let's take a look at the last one. How many electrons are in the bonds around that last one? Well, that's not much of a difference. So what do we do if we don't find a difference?
Go to the next.
Move to the next atom. When you move to the next atom, how many electrons does a carbon have? I'll accept a couple different answers on this. I can accept 6. How many electrons does the other carbon have? How about that other carbon?
You're not counting
Still
the
6.
carbons, the two.
We don't have to stress too much on exactly how we're counting it. We're just saying carbon comes in with 6 electrons. So how many electrons are around that carbocation in the bottom case? 18 electrons. Let's take a look at the top case. How many electrons does hydrogen come in with? 1. How many electrons are around that carbon? 6. Each hydrogen brings in 1, right? We get 3 electrons. Which can stabilize the positive charge better? 18 electrons or 3 electrons? 18 electrons. Which of these structures is more stable? The tertiary, because it has more electron density to stabilize that positive. This trend, you'll notice, works all the way through this. In that next one, you've got 8 electrons, and how we're counting this at least. And then the next one, 6, 12, 13 electrons. So progressively, as we put more carbons around our carbocation, it becomes more and more stable. Let's see how well you know this. What we could refer to as zeroary. I like to call it zeroary, though officially it's methyl. Here's your test. With the anions, which of those anions is the most stable? Why should the zeroary be more stable? It wants to be more positive, but we can't make it positive. We can't move positive charge. We want less electrons around it. Okay, so we can't shift the positive charge around, but we can change what's going on with the electrons. That's our primary difference. So in our zeroary, we have 3 electrons near that negative charge. In our tertiary, we have 18 electrons. Okay, which is more stable, putting more electron density in a tiny space or less electron density? We want less electron density. So the more stable one, when we move to the anion, ends up being our zeroary. Okay, so we see the opposite trend. Radicals, which is that middle section, are ultimately unstable because they're missing an electron, so they should act most like cations or anions. They're missing an electron, which means they should act most like cations, which is exactly what we end up seeing. Our radicals respond very, very similarly to our cations. Okay? So we can then take this in into consideration when we try and figure out our fragmentation patterns. So we've got an example mass spec here. You'll notice the peak furthest to the right, we want the tallest peak within 3 units. This case is nicely labeled for us, is labeled as 86. Okay, you'll notice that that is not the tallest peak. What does that mean? That piece is not very stable. That's it. That's all it means. Okay, so when we eject a single electron from that structure, that molecule says, I can blow apart into more stable pieces. So I'm not going to stay as this. I'm going to kick something else out. What's the most stable piece? The one at 43. What makes up the mass of 43? Carbons. Fair enough. How many carbons?
At least 3.
We're looking at 3 carbons. I agree with that. 3 carbons and 7 hydrogens. Where's the piece that accounts for 3 carbons and 7 hydrogens?
Secondary?
Putting our positive charge right there. What is special about that piece?
Secondary.
It is a secondary carbocation. Every other position, okay, ends up coming out as a primary once it cleaves. So we end up creating our most stable cation in that situation, which is why we see the largest concentration, or the largest amount of that piece. So we can actually predict something about the structure if we analyze those fragmentations. You could go through and do a similar argument with this guy. That signal at 55 is actually going to be due to, oh shoot, I don't think I remember this right. I think, come back, come back, come back. Wizard of Oz? No? Okay. Due to that piece, somebody left, that's good. We're looking at a radical with resonance stabilization. I can move the electrons of the pi bond and shift those around to stabilize that. Sorry, not a radical, our carbocation. We can do resonance to stabilize that carbocation. That piece ends up being our most populous piece because of it. Okay? So you can go through and evaluate the fragmentation patterns. I did put some questions like this within sapling. They're giving you the structure and they're saying, this is the signal that you see. Explain that signal. All right, that's what I would expect you to do with your fragmentation. At no point will I give you a mass spec and then say, this signal shows up at 55, tell me what the piece is, or tell me what the structure is from your mass spec alone. Okay, you will have to be given all this other information. Okay. I'm not going to ask any questions because we're down to like 3 minutes and I'd like to get through most of the NMR. And NMR is nuclear magnetic resonance, which means what we are looking at in NMR is the nucleus and its magnetic moment. Okay? Certain nuclei have a magnetic field. Okay? So what we can do is take those nuclei and put them in a larger magnet. They're now going to interact with that larger magnet. Okay? That interaction we can then mess with. Okay? We're going to mess with it by firing radio frequencies at it. The radio frequencies will knock our atoms off of the magnetic field axis, and we can actually time the amount of time it takes for them to come back to being in alignment with the magnetic field. Okay, I know it's kind of odd, but that's ultimately what's happening. So what we're concerned about is how those nuclei adjust within this. We end up with 2 energy states, a high energy and a low energy. Ultimately, again, not all that important. But what we're concerned about is that we've got these magnetic states that we are tweaking within the magnetic field of our instrument. Okay? What's going to end up changing or making this useful is that electrons now have the ability to hide the nuclei. So if I put a bunch of electron density around that nucleus, I'm going to have to use a higher energy radio frequency to get to that nucleus. Okay? Because the electrons kind of shield it from the radio frequencies. Okay? Because I'm using a higher energy, I can now correlate that to and say, well, that atom or that nucleus has a bunch of electron density around it. Or maybe it's really easy to get that nucleus to spin off axis. If that's the case, there's no electron density around it. How could I possibly get to the situation where there's no electron density around an atom? How can we have something remove electron density away from an atom? Are there, say, maybe any elements on the periodic table who actually take electrons away from other atoms based on their electronegativity? The closer our desired atom that we're analyzing is to an electronegative element, the less electron densities around it, we end up seeing a larger shift. Okay? That's what's contributing to our chemical shifts. It's that electron environment that's either hiding our nucleus or exposing it to the magnetic field. Okay? So all the principles that go through our chemical shift, our splitting, our integrations, all of those are dependent back on the same ultimate concept. Okay? In the actual spectrometer, we take a giant magnet, we drop our sample into that magnet. We've got our detector that can detect changes in the magnetic field, and then we can fire our radio frequencies through our RF transmitter, and then that gets converted by our computer into an actual signal that gets printed out, and then you get to analyze. Okay? This happens to be one of the larger magnets. It's 850 megahertz. That NMR is that tall. I don't know if you can quite tell that. That's roughly 20 feet tall. Okay? So it's a massive, massive instrument. Most magnets that get used are in the 300 megahertz range. So you're looking at a magnet that's probably only about chest height on me. Okay? You can get to smaller frequencies as well, or smaller magnetic fields that give you even less data and are a little bit smaller as well. So we're definitely out of time. But I think I've only got a couple more slides. So I'm going to stop there.